Analysis of variance involved examining the relationship between a categorical explanatory variable and a quantitative response variable. Next, we're going to consider inferences about the relationships between two categorical variables. The statistical test that will answer this question is called the chi-square test of independence. Chi is a Greek letter that looks like a large X, so sometimes you'll see this test denoted with an X squared. For this statistical tool, let's start with a new example. In the early 1970s, a young man challenged an Oklahoma state law that prohibited the sale of 3.2 beer to males under the age of 21, but allowed its sale to females in the same age group. The case was ultimately heard by the U.S. Supreme Court. The main justification provided by Oklahoma for the law was traffic safety. One of the three main pieces of data presented to the court was the result of a random roadside survey that recorded information on gender and whether or not the driver had been drinking alcohol in the previous 2 hours. There were a total of 619 drivers under 20 years of age included in the survey. On the left, you can see what the collected data look like, and on the right is a two-way table summarizing the observed counts in the roadside survey. Our task is to address whether these results provide evidence of a significant or statistically meaningful relationship between gender and drunk driving. Both variables are two-valued categorical variables, and therefore our two-way table of observed counts is a 2x2. The chi-square procedure is not limited to 2x2 situations. It can also be used for a larger number of explanatory categories. The key to reporting appropriate summaries for a two-way table is deciding which of the two categorical variables plays the role of the explanatory variable and then calculating the conditional percentages separately. That is, the percentages of the response variable for each value of the explanatory variable. In this case, since the explanatory variable is gender, we would calculate the percentage of drivers who did and did not drink alcohol for males and for females separately. Here's the table of the conditional percentages.
For the 619 sample drivers, a larger percentage of males were found to be drunk than females, 16% versus 11.6%. Our data, in other words, provides some evidence that drunk driving is related to gender. However, this in itself is not enough to conclude that such a relationship exists in a larger population of drivers under 20.
We need to further investigate the data and decide between the following 2 points of view: that there is no difference in the drunk driving rate between males and females under 20, our null hypothesis, or that there is a difference in the drunk driving rate between males and females under 20, our alternate hypothesis. In other words, is the evidence provided by the roadside survey, 16% versus 11.6%, strong enough to conclude beyond a reasonable doubt that it must be due to a relationship between drunk driving and gender in the population of drivers under 20? Or is the evidence provided by the roadside survey not strong enough to make that conclusion? And could this have happened just by chance? That is, due to sampling variability and not necessarily because a relationship exists in the population. These are the null and alternate hypotheses for chi-square test of independence. Here are other ways that the null and alternate hypothesis can be stated for a chi-square test of independence. There is no relationship between the two categorical variables. They are independent. Or, there is a relationship between the two categorical variables. They are not independent. Algebraically, independence between gender and driving drunk is equivalent to having equal proportions of who drank or did not drink for males versus females. In fact, the null and alternate hypothesis could be reformulated as the proportion of male drunk drivers is equal to the proportion of female drunk drivers, or the proportion of male drunk drivers is not equal to the proportion of female drunk drivers. The idea behind the chi-square test of independence, much like the analysis of variance, is to measure how far the data are from what is claimed in the null hypothesis. The further the data are from the null hypothesis, the more evidence the data presents against it. Here, the gender and drunk driving data are represented by the observed counts. To represent the null hypothesis, we're going to calculate another set of counts, the counts that we would expect to see instead of the observed ones if drunk driving and gender were really independent, that is, if the null hypothesis were true.
For example, we actually observed 77 males who drove drunk. If drunk driving and gender were really independent, if the null hypothesis were true, how many male drunk drivers would we expect to see instead of 77?
We'll also ask the same kind of question about the other 3 cells in our table. If the null hypothesis were true, how many female drunk drivers would we expect to see instead of 16? How many non-drunk driving males would we expect to see instead of 404? How many non-drunk driving females would we expect to see instead of 122?
In other words, we will have 2 sets of counts: the observed counts, that is the data, and the expected counts if the null hypothesis were true. We will measure how far the observed counts are from the expected ones. We will base our decision on the size of the discrepancy between what we observe and what we would expect to observe if the null hypothesis were true. How are the expected counts calculated?
If events A and B are independent, then the probability of A and B equals the probability of A times the probability of B. We use this rule for calculating expected counts 1 cell at a time. Applying the rule to the first top left cell, if driving drunk and gender were independent, then the probability of being drunk and male is equal to the probability of being drunk times the probability of being male. By dividing the counts in our table, we see that the probability of being drunk is equal to 93 divided by 619, and the probability of being male is 481 divided by 619. So, the probability of being drunk and male is 93 divided by 619 times 481 divided by 619. Therefore, since there are a total of 619 drivers, if drunk driving and gender were independent, the count of drunk male drivers that we would expect to see are the following, circled here in red. So the formula for calculating expected counts is column total times row total divided by table total. Following this formula, here are the complete tables of expected and observed counts. Importantly, the single number that summarizes the overall difference between observed and expected counts is the chi-square statistic, denoted as chi, or x squared, which tells us in a standardized way how far what we observe, that is the data, is from what we would expect to observe if the null hypothesis were true. Here's the formula. For each cell, we take the observed count, subtract the expected count, and square that value. This value is then divided by the expected count, and then this number is summed for all of the cells in the table. Once the chi-square statistic has been calculated, we can get a feel for its size. Is there a relatively large difference between what we observe and what the null hypothesis claims, or a relatively small one? It turns out that, for a 2x2 case like ours, we're inclined to call the chi-square statistic large if it's larger than 3.84. Therefore, our test statistic is not large, indicating that the data are not different enough from the null hypothesis for us to reject it. For cases other than a 2x2, there are different cutoffs for what's considered large, which are determined by the null distribution in that case. Thus, we're going to rely only on the p-value for conclusions. Even though we cannot really use the chi-square statistic, it was important to learn about it since it encompasses the idea behind the test. The p-value for the chi-squared test of independence is the probability of getting counts like those observed assuming that the two variables are not related, which is what is claimed by the null hypothesis. The smaller the p-value, the more surprising it would be to get counts like we did if the null hypothesis were true. Technically, the p-value is the probability of observing a chi-square at least as large as the one observed. Using our statistical software, we'll find that the p-value for this test is 0.201. A p-value of 0.201 is not small at all. There's no compelling statistical evidence to reject the null hypothesis, and so we'll continue to assume it may be true. Gender and drunk driving may be independent, and so the data suggests that a law that forbids sale of 3.2% beer to males and permits it to females is unwarranted. In fact, the Supreme Court, by a vote of 7-2 majority, struck down the Oklahoma law as discriminatory and unjustified.
Now we're going to use the chi-square test of independence to test the hypothesis I proposed about smoking frequency and nicotine dependence from working with NESARC data. Specifically, is how often a person smokes related to nicotine dependence among current young adult smokers? Or in hypothesis testing terms, is smoking frequency and nicotine dependence independent or dependent? That is, are the rates of nicotine dependence equal or not equal among individuals from my different smoking frequency categories? For this analysis, I'm going to use a categorical explanatory variable with 6 levels, the number of days smoked per month, which you may remember I called US Freak MO, with the following categorical values: smoking approximately 1 day per month, 2.5 days per month, 5 days per month, 14 days per month, 22 days per month, and 30 days per month. My response variable is categorical with 2 levels. That is, the presence or absence of nicotine dependence in the past 12 months, called tab 12 MDX in the NESARC dataset. To run this in SAS, we need only to extend our frequency procedure. We include procfreq semicolon, the table statement, our categorical response variable, asterisk, our categorical explanatory variable, followed by a /, and the abbreviated term for chi-square, CHISQ. Again, ending the command with a semicolon, and then saving and running the program. The SAS results for a chi-square include a table of the response variable by the explanatory variable, and also a calculation of the chi-square statistic along with the associated p-value. Looking back at the chi-square table, also known as the crosstabs or cross-tabulation, you can see a myriad of numbers and percentages with such labels as frequency percent, row percent, and column percent. Our p-value of 0.0001 clearly tells us that smoking and nicotine dependence are associated.
A chi-square table can be very confusing on first examination. Before we try to interpret this output, let's look at 3 different tables that pull apart the different numbers represented in a crosstabs. For our example, we're going to use percentages from a chi-square table examining the distribution of insured and uninsured individuals by geographic region. Table A shows row percentages. Each cell includes the percent of observations within each row, that is, within region Northeast, Midwest, South, and West, that are either insured or uninsured.
As you can see, adding across the rows gives us 100% of the observations within region. Table B includes the total percent of observations in each cell. Here, the percentage in each row and column add up to 100%. Finally, Table C shows column percentages. Each cell includes the percent of observations within column that is within groups, either insured or uninsured. Adding down the columns gives us 100% of observations by insurance status.
So which of these percentage types should we examine when trying to interpret the chi-square results for smoking frequency and nicotine dependence? If the output is set with the explanatory variable categories across the top of the table, and response variable categories down the side, it will be the column percents that we want to interpret. In other words, we're interested in whether the rate of nicotine dependence differs according to which explanatory group the observations belong to, that is, which smoking frequency group. Notice that we're not interested in the column percentages for those observations without nicotine dependence, indicated with a dummy code of 0. Instead, we're interested in describing the presence of nicotine dependence within the smoking frequency groups, that is, these column percentages circled with blue.
If I use SAS code to graph the percent of young adult smokers with nicotine dependence within each smoking frequency category, I could visualize the association and see that there seems to be a positive linear relationship. That is, the more days per month a young adult smokes, the more likely they are to have nicotine dependence. I know from looking at the significant p-value of 0.0001 that I will accept the alternate hypothesis that not all nicotine dependence rates are equal across smoking frequency categories. If my explanatory variable had only 2 levels, I could interpret the 2 corresponding column percentages and be able to say which group had a significantly higher rate of nicotine dependence. But my explanatory variable has 6 categories, so I know that not all are equal, but I don't know which are different and which are not.
When the explanatory variable has more than 2 levels, the chi-square statistic and associated p-value do not provide insight into why the null hypothesis can be rejected. It does not tell us what way the rates of nicotine dependence are not equal across the frequency categories. There are, of course, many ways for the rates to be unequal. Having each of them as unequal to the other is just one of them.
Maybe there are only 2 of the population rates that are not equal to one another. To determine which groups are different from the others, we will again need to perform a post hoc test. By conducting post hoc comparisons between pairs of rates in a way that avoids excessive type 1 error, in other words, avoids rejecting the null hypothesis when the null hypothesis is true, we will be much better able to appropriately describe which population rates are different from the others. I would really love to tell you that the post hoc paired comparisons are as easy to conduct in the context of chi-square tests of independence as they are in the context of ANOVA. Unfortunately, though, the task is a bit more arduous. There is no built-in follow-up multiple comparison test available for this procedure. If we reject the null hypothesis, we need to perform comparisons for each pair of nicotine dependence rates across the 6 smoking frequency categories. In the case of 6 groups, we actually need to perform 15 pairwise comparisons. With these red brackets, I'm illustrating 15 paired comparisons that we'll need to conduct. As you can see, there are so many, it's actually difficult to illustrate this graphically.
If you'll recall, the family-wise error rate for 15 different comparisons is 0.54. This means that if we do not protect against type 1 error, we will be wrongly rejecting the null hypothesis and saying that there's an association over half the time. Having about a 50-50 chance of being right would obviously give us absolutely no confidence in our decisions.
So, to appropriately protect against type 1 error in the context of a chi-square test, we will use the post hoc approach known as the Bonferroni adjustment. The goal of using the Bonferroni adjustment is to control the family-wise error rate, also known as the maximum overall type 1 error rate, so that we can evaluate which pairs of nicotine dependence rates are different from one another.
Briefly, the process would be to conduct each of the 15 paired comparisons, but rather than evaluating significance at the p.05 level, we would adjust the p-value to make it more difficult to reject the null hypothesis. The adjusted p-value is calculated by dividing p.05 by the number of comparisons that we plan to make. So if we make 3 comparisons, we would only reject the null hypothesis if the p-value were 0.017 or less. For the 15 paired comparisons that we plan to make to better understand the association between smoking frequency and nicotine dependence, our adjusted p-value is 0.003. Adjusting the p-value is definitely the easy part of the process. Now for the more challenging piece. For the actual post hoc testing, we need to run a chi-square test for each of the 15 paired comparisons. To do this, I can add syntax to my program at the end of the data step, just before the proc sort statement, where I choose 2 smoking frequency groups at a time. So I'm going to start by comparing my usual smoking frequency per month group 1 and my usual smoking frequency per month group 2.5. If I save and run this program, I get a new chi-square table that includes only those 2 frequency groups by the presence or absence of nicotine dependence. Again, I want to focus here on the column percentages, 9.86 and 18.46. Are these 2 rates significantly different from one another? If I look down at my chi-square value and probability, I can see that they aren't. So I want to accept the null hypothesis since this probability value is not only not less than 0.05, it is definitely not less than my Bonferroni adjusted p-value of 0.003. Going back to my graph showing the rates of nicotine dependence for each smoking frequency group, similar to the notation that was used in the Duncan post hoc test in the context of ANOVA, I'm going to designate the first 2 rates with the same letter, that is a capital A, indicating that they do not differ significantly from each other. This is just the first step in our post hoc analysis. Now we need to run 2 by 2 chi-squares for each of the remaining 14 paired comparisons.
To do this, we could continue 1 comparison at a time, choosing 2 frequency groups, by adding syntax to the program at the end of the data step and just before the proc sort statement. Here's the syntax requesting a chi-square analysis comparing those smoking 1 day per month and those smoking 6 days per month. Per our code, we can see that only smoking frequency groups equal to 1 and equal to 6 are included in the chi-square table and analysis. The nicotine dependence rates are 9.86 and 21.59. The p-value associated with the chi-square statistic is 0.0468. Initially, we might want to say that this is a significant finding because it's less than a p-value of 0.05. Remember, though, that the adjusted p-value for these comparisons is 0.003, so this is not significant. Going back to the graph of nicotine dependence rates, we now know that frequency group equal to 1 and equal to 6 do not have significantly different rates of nicotine dependence. We'll illustrate this by again adding the same letter to the smoking frequency group equal to 6. This could get pretty tedious, and of course it would be very easy to get a bit confused and to skip 1 or more paired comparisons. Let's look at how to use syntax that you already know to do this systematically and to get results for all of the paired comparisons simultaneously. First, we'll get rid of the lines of syntax that subsets our data to specific smoking frequency groups. Now, we'll create a series of new data sets and associated chi-square tables that call in the original working data set and select each of the various combination of smoking frequency groups. We've just added quite a bit of syntax to this program. You'll see, however, that it's repetitive and that in each group of syntax, only the logic statements that select the specific frequency groups and the working data set name need to change. Following the data step and the request for output that we've been working with, we're going to add a new data step and call it comparison 1. We set the original working data set, which was called new above, and then subset the data to the 2 smoking frequency categories, smoking frequency category 1 and 2.5. We end this data step by sorting by the unique identifier and requesting a chi-square analysis with the proc freq procedure. Then we end this new syntax group with a run statement. Next, we repeat those same lines of syntax for each of the remaining 14 paired comparisons, changing only the name of the new working data set and the selected smoking frequency groups. Copy and paste works very well when creating numerous new data sets for post-hoc comparison tests. It's good for avoiding typos that can compromise your program. Here, we call the data comparison group 2 and select smoking frequency group 1 compared to smoking frequency group 6. Here, the data is comparison 3, and we're comparing smoking frequency group 1 to smoking frequency group 14. Comparison group 4 is comparing smoking frequency group 1 and smoking frequency group 22. We see these lines of syntax repeated with new data names and the additional paired comparisons for the smoking frequency groups all the way down to comparison 15, smoking frequency group 22 versus smoking frequency group 30. When we run this program, the results include the overall chi-square table, that is, the 6-level smoking frequency variable by the nicotine dependence response variable, and then chi-square tables for each of the paired comparisons, 1 versus 2.5, 1 versus 6, 1 versus 14, 1 versus 22, 1 versus 30, 2.5 versus 6, and so on. The goal is to examine the p-value for each of the paired comparisons and to use the adjusted Bonferroni p-value of 0.003 to evaluate significance. Here, we've created a table that shows the p-values for each of the paired comparisons from the output. Obviously, there are several that are less than p is 0.05. Here are the p-values that are less than 0.003. As we can see, smoking frequency group 30, that is, those who smoke 30 days in a usual month, is significantly different from each of the other smoking frequency levels. In addition, smoking frequency group 1 has significantly different nicotine dependence rates than smoking frequency groups 14 and 22. Using the letter convention, in which nicotine dependence rates with the same letter are not significantly different, these post-hoc findings can be pictured like this. Here's another way we could picture the significant differences between rates. As you can see, the more differences there are, the more challenging the visualization can be to create. Let's quickly summarize chi-square tests of independence. First, a chi-square test of independence is used when we have a categorical explanatory variable and a categorical response variable. The null hypothesis is that there is no real relationship between the two categorical variables. They are independent. And the alternate hypothesis is that there is a relationship between the two categorical variables, and they are not independent. The chi-square statistic is calculated considering both the observed and expected counts in each of the table cells. The model SAS syntax for performing a chi-square test of independence is proc_freq semicolon tables categorical response variable asterisk categorical explanatory variable / CHISQ semicolon. If your explanatory variable has more than 2 levels or groups, you'll also need to conduct a post-hoc test. We use the Bonferroni adjustment to protect against type 1 error and then run the chi-square tests of independence for each paired comparison. Now you're ready to test a categorical by categorical relationship. Also, if your own research question is a quantitative to categorical relationship, it's a good idea for you to categorize the quantitative explanatory variable and test the association with the chi-square test of independence.